Okay, so we're going to have a look at the GCSE Group 7 Chemistry. This is part of your periodic table topic, which is Chapter 3 of the textbook. So I'm starting today on the particular part of that textbook. I'm going from page 43, bottom sort of half of page 43, and this will take us through to the sort of the top part of page 49, guys. So if you want to have your textbook and go to those pages, or alternatively you can read them after and make sure that you do the little test yourself questions. And I would also say to you then, you've got some end of chapter questions as well on page 53 and page 54 to accompany this topic, and the one that is any questions on that are regarding group 7. Let me see, you've got question 5 there, part of question 5, which you can do, and also check, and that's part of group 7, a little bit of question 8, also question 8a there is to do with group 7. Okay, so let's get started with this. Alright, so group 7, obviously we've done a certain amount of the periodic table. We've done the general geography of the periodic table. We have also looked more specifically at group 1 of the periodic table, which is the metals, and we're going to look now at the group 7, which is the halogens, which are essentially non-metals this time. Okay, so let's have a look at introduction first of all. So you should have a fairly good idea now of the geography of the periodic table. What's on the board now, what's on the screen should look fairly familiar to you. You've got your vertical columns, which are your groups, and you've got your periods running horizontally. And within that then we have a period called the halogens. We can see those halogens highlighted obviously in purple here, and those are group 7, and they're all in the same group because they all have the same number of electrons in their outer shell. And if they all have the same number of electrons in their outer shell, that means that they all are able to react in a very similar way. That's why they're put in the same group. Okay, so how many electrons do they have in their outer shell? Well, they all have, of course, group 7 electrons in their outer shell, meaning that they will all want to gain 1 electron in order to get their full outer shell, and that's how they all react. Okay, the ones that we'll particularly focus on in this are chlorine, bromine and iodine. You'll have to predict a little bit about the properties of acetane at the bottom. We might do a little bit about fluorine, but predominantly we'll look at chlorine, bromine, iodine. Okay, so those are the 4 main ones. Acetane at the bottom. I think acetane is like one of the most rare elements on Earth. I think there's been less than 1 milligram of acetane ever actually made. So it's a phenomenally rare thing. It's very radioactive. Only see it or get it really in nuclear power stations. So it's not the sort of thing you'll ever deal with in the lab. Let's have a quick look at some of the properties. You do need to know a little bit about the properties. You can see a guy frying an egg here, and that's because that's to do with fluorine. Fluorine is used in the non-stick. Fluorine is not used to make eggs, by the way. It's used to make the surface of a non-stick frying pan compound. You can see it there on the screen. A compound called Teflon. Okay, and that means that things don't stick to the surface. It's a compound made by the combination of carbon with fluorine. Okay, so chlorine then, you should know a little bit about chlorine. You'll know it's used in bleach. You can see the guy with bleach. It's very smelly. Whenever you're bleaching your floor, you can get a very pungent smell off it. It's very good at killing bacteria. That's why it's used in bleach and disinfectants. But you have to remember it is extraordinarily dilute in that environment. So it was actually used as a chemical weapon in World War I. In a much more concentrated gaseous form. So if you breathe chlorine in, it's extremely toxic and lethal. Bromine then is a phenomenally strong, horrendous smelling. It's a orangey brown liquid which turns into a gas easily at room temperature. Used to be used to dye Roman emperors' togas. Looked very dashing when the toga was dyed with bromine. It came out a purple colour. Unfortunately, it was highly toxic, which they found out later. Iodine used in silver iodide, which can be used whenever there is a complete lack of rainfall in certain parts of the world. You'll see aeroplanes going up and spraying silver iodide crystals into the air, which causes the moisture in the air to accumulate around them, and it gets so heavy that it falls to the earth as rain. So it's a good way to induce some rain. And then acetylene, as I said earlier, highly radioactive, comes from radioactive decay of uranium, an extraordinarily rare compound, or element, sorry, not compound. Okay, so if we look, that's a couple of them there. That's bromine. We have some bromine on the left there. Again, you can see it's an orange liquid, orangey brown liquid there, and it very easily turns into gas. Very, very volatile. Okay, the bromine. And then we have down here, we've got iodine. Everyone thinks of iodine as sort of a brown liquid, and that's because you see it on TV as a brown liquid in hospital programs where they use it to disinfect wounds and kill bacteria. Actually, pure bromine on its own is a grey solid. It's only whenever it's dissolved up in water or solution that you actually see it as that brown liquid. So if you're asked what its iodine is like, you're talking about the pure form of iodine. And they're using antiseptics, as I said. They're very nasty elements, and they kill bacteria essentially. Okay, so we don't ever find these halogens, we've said down here, we don't ever find halogens pure and uncombined in the environment. We don't find them in the air, we don't find them in rocks or the soil or the earth or the crust of the earth as uncombined elements, because they are extremely reactive. We find them in generally in halogen metal compounds called salts. Okay, in fact, the word halogen comes from the Greek word which means salt former. Okay, so you'll find when I talk about salts, things like sodium chloride, potassium bromide, that's the sort of thing we're talking about there, and that's how they're found. Okay, right, so all of them have 7 electrons in their outer shell, as we said earlier. So they all want to gain 1 electron from somewhere to get a full outer shell, and in doing that, they will become a -1 ion. And you'd have done this whenever we did our ionic bonding topic. Okay, and that's what gives them all the similar chemical properties. So you'll have to be able to write half equations for the formation of the halide ions from the halogen themselves. So I've given you a little general equation just here. You can see it, and I've asked you to complete it for chlorine. So if I completed it for bromine, for example, bromine we know is, of course, diatomic. You should know that pure bromine we always write as Br2. It turns into halide ions, okay, and I've got my electrons on the wrong side there, I've just noticed. I'll change that. Okay, it turns into halide ions, so 2 Br minuses. What does it do to get that? It has to gain electrons, as we said on the last slide, but remember, it's going to have to gain 2 electrons. Now, the alternative way of doing that, you can do, if it's a diatomic, have half of a diatomic. So you could do half Br2 plus 1 electron goes to a bromide ion. Okay, either of those will be absolutely fine. Okay, so if you pause the video, write your answer for chlorine, and then I'll put chlorine on up here. So pause the video now and do it. So Cl2 gains 2 electrons to go to 2 chloride ions. Alternatively, as I said earlier, you could have half of a chloride plus 1 electron goes to a Cl minus, a chloride ion. Okay, make sure you get your electrons on the right side. Okay, so to become stable, they all get that full outer shell by gaining 1 electron. They can also get a full outer shell by sharing 1 electron with another non-metal. So for example, you can see 2 fluorines here. And again, when we did our covalent bonding topic, you guys should be really very familiar with this. The fact that 1 electron from that and 1 electron from that can be shared, and we have F2, and if we were to do it with our little line diagram, we have F with our single line showing a single covalent bond, a sharing of 1 pair of electrons. Okay, so you know that all of the halogens exist as diatomic molecules, so when you're writing them on their own, make sure that you do that. Okay, so you have to know in GCSE chemistry the test for chlorine. Okay, that's the only one of the halogens that you need to know the test for. So chlorine is a bleach, but it also forms an acidic solution. So what we do is we start off with some damp blue litmus paper, and when you're writing the answer to this, you must make reference to the fact that the litmus paper starts off as damp. That litmus paper, when you dip it into the chlorine, goes red because it's acidic. Okay, and then finally it will bleach it to to a white colour. So that's your test. If you have a gas or a solution which contains chlorine, and you think it contains chlorine, you dip some damp blue litmus paper into it. If it originally turns red and then it turns white, it gets bleached white, that's proof that you have indeed got some chlorine in that solution. Okay, so let's look at the physical properties then of these group 7s. So they don't conduct electricity, they are brittle, they are crumbly. If they are solid, that only applies to iodine. They don't conduct electricity because non-metals, when we did our covalently bonded substances earlier in the year, we knew that they have no free electrons, no free ions. They're very poisonous and they have an extremely toxic smell, and they become darker as you go down the group. So fluorine's a very pale yellow gas, chlorine's a slightly greener yellowish gas, bromine is a dark orangey brown liquid, turns into an orangey brown gas very easily at room temperature, and iodine is dark grey solid at room temperature. Now, iodine has this rather strange property in that it sublimes easily at room temperature to turn it, or not at room temperature, when heated, sorry, into a purple gas. Now it goes straight from a solid to a gas. It does not form a liquid en route. And that's what sublimation or subliming means, that it goes from solid straight to gas without becoming liquid. Acetane, which you don't have to know, but you may be asked to predict what it's like. So it just continues the trend of becoming darker and becoming more solid. So it's almost a black solid at room temperature. Okay, so let's look at the physical properties then of these things as the relative size of them increase. So you can see as you go down the periodic table, they get much bigger, the density gets much greater, and you can see they easily turn from, you can probably start to see now why fluorine here is a gas. Chlorine's a gas, very low density, and then we're getting into our liquids, higher density, and then into our solids, even higher density again. Okay, so what I'd like you to do is to complete this little table here, similar to one of the ones that we did when we were doing structures at the end of our bonding topic, to find out the melting point and the boiling point of these particular elements, and to work out then whether they are solids or liquids or gases at room temperature based on that. So pause the video and go and research that, either online probably, and come back and fill those in, or check your answers. So pause the video now. Okay, so you can see there, those are the trend and melting point. Hopefully you can see as we go down the table, melting point and boiling point both are increasing, turning these things from gases into solids. Okay. Okay, so let's look at the reactions of and the reactivity of the halogens. So you need to know some of the reactions and be able to write balanced simple equations for them, and then discuss the change in reactivity of the group 7 halogens in the same way you discussed the group 1 metals reactivity. So we already know that they all, the halogens gain 1 electron in order to get the full outer shell to become stable. So we should all be familiar with this type of thing here, where we have our sodium, which starts off at 281 electron configuration, our chlorine, which starts off at 287 electron configuration. 1 electron moves from the sodium to the chlorine, this electron here, and we end up with a full outer shell of 28 in our sodium and a full outer shell of 288 in our chlorine, giving our sodium a +1 charge, and our chloride, now as we call it, -1 charge, and that's the ionic bond, the positive to negative attraction. Okay, the other way that these things can gain a full outer shell, as we said earlier, is the sharing of an electron, but this time remember it's with a non-metal. So in this instance it's of course hydrogen, and that's a single covalent bond, and we can represent that by a line, a single line. Sorry, I don't know what happened there. Okay, so we can represent it just as H, single bond, Cl, where we have 1 pair of electrons. Okay, so if you could pause the video now, guys, and write some balance symbol equations for the reactions of that I've put on the board there for those. And I'll put the answers up, and then you can check them. So remember, chlorine is diatomic. Fluorine on its own is, of course, diatomic. Okay, they both will share one electron each to give that, and therefore I need 2 on the left hand side to balance it up. Oxygen is also diatomic. Fluorine is diatomic. Now if I draw the dot cross diagram, excuse me, the dot cross diagram for this, I will see that oxygen, if you remember, needs to share 2 of its electrons to get a full outer shell. So I will have F X dot. Oxygen has 6 in its outer shell, so we'll leave 4 on it there, and we can see now that the oxygen has a full outer shell, and the fluorine, has 7. So 6 crosses plus the one that's in the bond, and the same on the left hand side. Okay, and then we can see that fluorine also has a full outer shell, so that would be F2O. We need to balance that then, so we're going to need 2 there, a 2 there. Okay, and that's it, balanced. Okay, the last one then, if we remember that the way to work out, I suppose I should just remind you guys, is that oxygen has a combining power of 2, fluorine has a combining power of 1, so when we do our swap and drops, that becomes F2O. So that allows you to work out the formula of it before perhaps you do the dot cross diagram. Here obviously fluorine is a combining power of 1, chlorine combining power of 1. Okay, let's just do the same here, carbon and chlorine, so carbon and chlorine. Carbon, remember, is 4, chlorine is 1, so that's CCl4. Okay, so we take our carbon, we're going to write do the dot cross just to show you how that sets up. Carbon is in the middle, chlorine, 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 and each chlorine, I'll not draw them all on here, but each chlorine has its 7 crosses. Okay, and if we look at our carbon then, we just have got our 8 electrons that are being shared. So it has got its 8 electrons in its outer shell, and that means we have Cl, single bond, Cl, single bond, Cl, single bond, okay? And our formula is CCl4. If we go over here, when we write the balance symbol equation, we've got carbon plus 2 Cl2s gives me CCl4. Okay, so that would be the balance symbol equation. Okay, now, the halogen atoms, we've already said, they become negative ions, they gain an electron, and when they do that, they are no longer referred to as halogens, they're called halides. And you need to know the halide that is made from the particular halogen. So fluorine goes to fluoride, which is a -1, chlorine to chloride, bromine to bromide, and iodine to iodide. You should know those all already anyway, but just to remind you. Okay. And again, as we said earlier, if they're combining with the group 1 metal, okay, the group 1 metal loses its electron from there, which goes to there, and that we can account for that as a little cross in the outer shell of the chlorine, and we get a -1 and a +1. And again, that's just a little bit of refresher over your ionic bonding. Okay, and we now get our ionic bond, positive and negative attractions. Okay. Right, so we're going to write a few equations just for the metal and the non-metal now. We've done some equations with the metal and the metal. So write a balanced equation for the reaction between chlorine and sodium. So if you could just pause the video, write the balanced symbol equation for that, and then hit play again and just check your answer. So pause now. Okay, so again, just reminding guys that we had chlorine, okay, which is of course Cl2. Okay, and therefore, and remember our sodium over here is +1 and our chlorine is -1, so we have 1 to 1, which means we need to. Some people might write, forgetting that chlorine only has to be a 2 when it is diatomic pure chlorine on its own over here. Okay, do the same then for a word equation for potassium with bromine and a symbol equation both. Pause the video now. So there's the word equation, pretty straightforward, and there's the balanced symbol equation. Okay, let's look at another one, slightly different this time, chlorine with magnesium. So just be careful with regards to the balanced symbol equation here. So pause the video now. Okay, so this time we have magnesium plus chlorine going to magnesium chloride. Now remember, magnesium is in group 2 is 2 plus. Chlorine is 1-, so we need MgCl2. That rather nicely self-balances. Okay. The next one we have, I'm going to change that actually, sodium is to aluminium actually. Okay, so again, pause the video please and have a go at it. So remember, aluminium is 3 plus. Chlorine is still 1-, so it's AlCl3. So we're going to need 2 there and 3 there, and we're going to need a 2 there. The alternate way to do that would be Al plus, you can do, because they're diatomics, we can have half, 1.5 Cl2 goes to AlCl3. Okay? Right. What about the reactivity then of these elements as we go down the group? We already looked at that for group 7 or group 1, sorry, for the alkali metals. We know that trend in reactivity. We should know how to explain that trend. This is similar but opposite. So if you remember group 1, just so we refresh our group 1, the reactivity of group 1 metals as we went down the group, it increased. Okay, so that was our trend for group 1. Okay. The opposite is true for group 7 non-metals, that when we go down the group, reactivity decreases. So you need to be able to explain why this is. There's another video that looks at this in a little bit more depth, but this one here will give you enough information to answer it at GCSE. So as we go down the group, the elements get larger. There's more shells, so of course they get larger. We've just used fluorine and chlorine here as an example. And that means that the outer shell electron gets further away from the nucleus and is more shielded from the nucleus. Now when I talk about shielding, what I mean is the amount of electron shells between the nucleus and the outer electron. So in fluorine obviously there's just one shielding shell, whereas in chlorine there are 2 shielding shells. Okay? So the further out the outer shell is from the positive attraction of the nucleus, the harder it is to attract another electron. So remember, these elements are trying to gain an electron in order to get a full outer shell. Because the chlorine here has more shells and the positive nucleus is further from the outer shell than in the fluorine, the positive nucleus is closer to the outer shell and has a stronger attraction. Okay, that very simply means that our electron, okay, that this electron here will be much more strongly attracted to the nucleus of the fluorine than the nucleus of our chlorine in the bottom left hand or the bottom right hand corner here. Okay, so when you're explaining the change in reactivity down the group, you talk about the size of the atom as you go down the group, you talk about the distance of the outer shell from the nucleus, and you talk about the fact that it is more shielded because there are more electron shells in the chlorine versus the fluorine in this instance, and because of that it is harder to attract that electron that those elements need in order to get a full outer shell. Okay. Okay, so we've got a little checkpoint quiz here. Okay, so maybe pause the video and have a go at it, guys. And I'll put the answers up and then you can check that you are correct. So pause the video now, please. So it says here elements that they exist as monoatomic. They do not. They exist as diatomic, so that's incorrect. The reactivity of the halogens increases down the group. We've just established that it decreases. The halogens form negative ions. They do indeed. They form -1 ions. The halogens are gases. Well, that's not right because 2 of them are gases. 1 of them is liquid and 2 of them are solids. The halogens become darker as you go down the group. They certainly do. And halogens have 6 electrons in their outer shell. No, they don't. We would know by now that they have 7 electrons in their outer shell. So that's incorrect. Hopefully you did alright in that. Okay, so let's move on to the last part of this, which is displacement reactions, is the last thing that you need to be aware of. So within displacement reactions, there is what we call the displacement rule. Okay, this is the displacement rule. Make sure that you know it. So if a halogen is added to a solution of a compound containing a less reactive halogen, it will react with the compound to form a new one. That is displacement. Now, we'll look at some examples and that rule will hopefully become a little bit clearer. So, for example, we already know that the reactivity decreases down the group. So in this particular context, our 2 halogens are fluorine, and we know that fluorine is more reactive than chlorine. So if we go up to our displacement rule up here, we will see that the more reactive halogen will displace the less reactive halogen. Okay? So a reaction will happen, in other words. So displacement will mean that the fluorine will take the place of the chloride. So we can predict our products. Because fluorine is more reactive than chlorine, we get sodium fluoride. The chlorine is displaced, it is kicked out if you like, and we get chlorine. Now again, you'll be asked to write balance symbol equations to represent that. Remember, fluorine and chlorine on their pure form are diatomic. Remember, sodium is +1, chlorine is -1. Same for sodium and fluoride. Okay, and then remember to balance. We have 2 chlorines and 2 fluorines on each side. Okay, so the more reactive halogen will always displace the less reactive one. So here fluorine has displaced chlorine. Okay, and that's just what is happening. If you can see here, this is my sodium chloride here, what I had in my equation. Remember, my chloride has that electron that it has taken originally from the sodium, and remember my fluorine has got a greater attraction for electrons than the chlorine. So what happens here is that the fluorine, this electron, the fluorine takes this electron from there, that is now taken out of the chlorine, and I now have a fluoride ion and I have chlorine left behind. So those are my products. Okay, so we'll just go over that again because I think some people will find that a bit tricky. Okay. Okay, so originally this electron has come from the sodium and I've got sodium chloride. I bring fluorine into the equation, which has got fewer shells and a greater attraction for this electron. So it takes that electron away from the chloride, and it forms now F-1, the fluoride. This electron has now gone, the charge has now gone at 0, and I now have chlorine. So I went from sodium chloride plus fluorine to sodium fluoride plus chlorine, which is just what I had on my equation back on this slide. Okay, right. So let's look at what happens then in terms of these little half equations, and we sort of talked about these already in a previous slide. So if you look at the chloride that we started off with there, okay, the chloride has lost its 2 electrons. It gave them, remember, to the fluorine, okay, sorry, to the fluorine, and it's now become just chlorine. The fluorine that reacted with the chloride stole the electrons from the chloride, and now it's a fluoride. It's gained those electrons that were originally belonging to the chloride. So you have reduction going on here. Okay, the reason why this is reduction is because electrons have been lost. That's reduction reaction. And this is an oxidation sorry. Up here is oxidation, I should say, because electrons are lost. You can see the electrons over here. Down here we have reduction because my electrons have been gained. Okay, as you can see, the fluorine is gaining plus 2 electrons. That's called reduction. And when we get reduction and oxidation occurring together, we call that reaction a redox reaction. Okay, and that's a little way to remember that oil oxidation is loss of the electrons, oil rig, reduction is gain of the electrons. Okay. So let's have a look then at what happens when we mix a variety of these halogens with their halide ions. Okay, so we're going to take some potassium bromide, okay, and we're going to take some chlorine. So I want you to just sort of think, will a reaction happen here, and what might we see? What will be made, and what does that look like when it is made? So this is chlorine. It's a pale, very pale green liquid. I'm going to pop it into potassium bromide. So maybe pause the video, maybe write the equation, and think, what is the product going to be here, and what might that product look like when it's formed in a test tube? Okay, so what you can see is that the test tube turned a sort of a browny orange color. Okay, now the reason for that, okay, maybe you could think about the reason for it. We'll put some iodine in there. You can see that when I put the iodine in, it just stayed exactly the same color. There was no, the only color, the purple color in here is just the purple iodine being added to it. Okay, so what's happening? What do we think is actually going on? Well, if we look in the left hand one, okay, this one here, the chlorine is displacing the bromine. Okay, and if it's displacing the bromine, the browny color in here is because of the bromine forming. If we look over here, the iodine is less reactive than the bromine, so the iodine can't displace the bromine. Therefore, the only color change that we saw here was the color of the iodine being added to the potassium bromide. So in the right hand test tube, no reaction has occurred because iodine is less reactive than bromine. In the left hand test tube, the chlorine has displaced the bromine, and the brown color is the formation of the bromine that is in the test tube now. Okay. Right, so let's do some predicting as to whether displacement reactions will happen. So what will happen if bromine is added to sodium iodide? Well, the bromine will displace the iodide. Okay, because remember, bromine, the displacement rule, the bromine is more reactive than the iodine. Now, what color might you see in this test tube? Let's write a word equation, let's write a balanced symbol equation. So pause the video and do that. Okay, so our balanced symbol equation then, and our word equation would be bromine, Br2, plus sodium iodide, NaI, goes to NaBr, we need 2 of those, plus I2. Now use that then to predict what you might see. Well, we're starting off here with, in the test tube, sodium iodide. Sodium iodide is colorless. We're adding some sort of red-brown coloured bromine to it. We're making sodium iodide, which is colourless, but more importantly, we're making iodine, which is a very dark brown colour. Okay, and that very dark brown colour is what you will see in the test tube, and that's your observation. This test tube solution went from colourless to very dark brown because of the iodine that is made in there. Okay. Right, so I want you to fill in this or try and have a go at this. Okay, so you can see the answers here at the bottom. If you just work out which box it should go into, and then I'll place it and you can check it right. So I'll give you a few seconds, or you can pause the video, and then so if you pause the video now. Okay, so potassium bromide and iodine would be made in that one. Where is the iodine solution? Well, it should go in down here under the chlorine and the bromine. Potassium chloride and the bromine, where would that be made? Well, that's up here where the chlorine is displacing the bromine. No reaction, where would we get no reaction? Well, no reaction must be, well, there's a few places. Iodine will not displace any, so I can put no reaction in there. Okay. Potassium iodide solution should go up here. It must be in there because we're making iodine in both those reactions. No reaction here. Bromine can't displace the chlorine. And we put the potassium chloride up there. Okay, so that's, hopefully you were able to go through that and get that all correct. Okay, so a few questions we will do. Can you unscramble these words? Oh, sorry. Okay, so that one's diatomic. Let's go back to the last one. Oh. Next one. I think that's long enough. Halide. Let's do the next one. It's a long one, giving you a minute for that one. I'll give you about 30 seconds. To do with the last topic that we did just there now. Those last types of reactions, I think. Okay. Give you another couple of seconds on it there. Pause it if you still haven't got it. Okay, again pause it if you haven't quite got it yet. I'll give you the answer now. Hydrogen halide it is, behind that, well done. Okay. Right, so a few key terms and key words there, guys. And then we're into our quiz. Right, so again, pause it, I'll click on the answer and hopefully it shouldn't take you too long anyway. Okay, so first one is 7. Second one is D. Okay, so which one is it? A, B, C, or D? I'm going to pause the video, I'm going to give you the answer now. Okay, have a look at the, I'm going to give you the answer now. No, I'm not. Oh, we always read the question. Most reactive to least reactive. Okay. Okay, so which one will not result? So here we're looking for a displacement reaction which will not result in a reaction, or a reaction which will not result in a displacement reaction. So iodine is less reactive than chlorine, can't displace it. Okay. Okay, so which one? So I'll give you the answer now. Okay, I'll give you the answer now. So just a metal halide. So for example, sodium plus chlorine, sodium chloride. There's no hydrogen, no oxygen made in that. Okay, have a look at it. I'll give you the answer now. We have two non-metals, hydrogen and bromine are non-metals, therefore you get a covalently bonded substance. Okay guys, hopefully that helps. You've got your page references in chapter 4 there, so you're starting at page 43, running through to page, top of page 49 there, okay, and that should be a good talk through of your halogens.